Okay, so I'm going to try this. Let's pray to God and hope it works. Okay, so there's a technical presentation about running your Python scripts instead of through the normal C Python interpreter, running it through MicroPython. Not on a microcontroller, but even on regular OSs like Linux and Mac and whatnot, right? But before I can get into the technical presentation, I have to tell you something. A love story. So 12 years ago, I fell in love in 2006. I got married to my wife in 2005, but in 2006, I fell in love. Reason for that is I fell in love with Python. And, you know, when you fall in love with someone, you want to spend all your time with them and do everything with them, right? I'm going to try something. Maybe I'm playing with fire, but let's see what happens. So we did command line scripting together, web applications, GUIs, network programming, coroutines, you name it, we did it. Until one day, something came between me and my love, and that was Conky. So who here knows what or who Conky is? Oh, very good. 2. Cool, not bad. Oh, 3. 3 out of 1,600 attendees. Very nice. So Conky is a piece of software that runs on like a Linux desktop, and it lets you monitor your resources, your CPU and RAM and whatnot. And it's quite flexible in what it lets you do. It has 300 built-in widgets, and you can extend it. So I wanted to add some of my own little widgets, and I found 5 little scripts that I wanted slapped together. So naturally, I implemented it in Python. Now, I want it to check these little widgets and resources every second. And the way Conky works, it will spawn this process, get the output, and display it to you. So I said, whoa, if I have 5 of these, and I'm running this every second, then each day on my machine, I'm going to be spawning 400,000 Python processes. So this felt at the time like maybe it's a bad idea. So I just slapped together a quick hello world in Python bash, compared what's this going to do to my CPU. And I saw that if I did the same just dumb hello world in Python or bash, if you're running 5 of these every second, you know, the load that Python will put on your computer is more. So I said, that's fine. This is not what Python was meant for. This feels kind of messy anyway, spawning all these processes. So I used bash and moved on. And then over time, I discovered other places where as well, the way that software would integrate into Python and other languages is spawning these processes. So an example is in text editors like Vim and Emacs. Whenever you save your source code, it can go through a linter and show you syntax errors like flag 8. Also, when you're using the terminal and you want to do completion, bash completion for pip, let's say, pip supports that too. And it spawns a process every time you press tab. But I noticed in some of the software it's quite slow. So from a usability perspective, anything that takes more than 100 milliseconds, you're going to feel it a little bit like a lag or feel chunky. So Flake 8, for example, on my machine was taking more than 3 milliseconds. Pip at times take more than 1 second. So I knew about that. And then you'll see in this talk, we'll look at MicroPython, and we want to measure how much time, right, it takes for any script to run, start, and complete its execution. So I'll show 2 different ways of measuring execution time. And as I was doing this, I saw that the same exact script on the same interpreter might have very different execution times on 2 different machines. And the main reason was I had, my desktop and my laptop. The laptop was older than the desktop, and so it had a faster CPU, and that would throw the numbers off. So what we'll also look at is clock cycles, because when I measured clock cycles as well, I could see that at least in this case of Python starting, that the clock cycles are the same. So we'll look at that just as a measure to tell you how much load is it putting on the CPU. Then I thought, if we're going to compare Python and MicroPython, why don't we throw some other languages into the mix? So this is the test scripts that will be used to generate the benchmark information. And basically, I went for the dumbest, simplest type of script. Right? It's 1 line of code. It's going to evaluate an expression, add 1 and 1, and output 2 to the terminal. The first one, add.py, will be used to benchmark both Python 3 as well as MicroPython. Then we'll look at Bash, Perl, Lua, and Awk. And I intentionally chose to only compare Python to other interpreted languages, right? It would be unfair to compare it to Go or C that compile to machine code. So let's look at just the time. So if you run the time command as part of Bash, so it's available on Linux, BSD, and Mac. So when you run time in the command, the first number is what you care about. So in this case, it was taking 10 milliseconds. Nice and easy, seems to do the job, but it has two major issues, which is why I'll show the next method. One, the resolution of the time. It's only going to give you in terms of 1 millisecond. And you see later on that some of these scripts start up in less than a millisecond. So you're not getting very accurate numbers. The second thing is it's only taking one sample, right? When you want to benchmark, you want to take a bunch of samples, take the average, the variance, and everything, so that you get something that's statistically meaningful. So this is the command of choice on Linux systems, at least. It's called perf. It comes with, you can install it with Linux on Linux distributions. And it has a subcommand called stat. So similar like time, I mean, you just put the command that you'd like executed, it will run it. It has one command line option that I definitely recommend using, -r, which you can specify how many runs of this do you want. From the output, I've highlighted in red some of the items of note. So you see we're running 10 runs. The other thing is 0 context switches. So what that's about is as you're running your test, your workload, was the CPU switching out to other processes, which will not give you accurate numbers. In this case, it's 0. So that's what you want. You want when it runs to get 0. And the takeaway from this is you don't want to be running this on a server with databases and web servers and application servers and a lot of noise. You'd like to run it on hardware that isn't running too much else as you're running your benchmarks. And finally, we can see that in this case, to add 2 numbers in this script and load the interpreter, it took 31 million CPU cycles. And the number we care about the most is at the bottom left. It's showing that this executed 9.3 milliseconds. Now, what's great is if you look at the accuracy of the number, it's up to a millionth of a millisecond. So it can give you very accurate kind of figures. The last thing of note is the 0.25%. What that is it's saying, OK, I took 10 samples. The average of those 10 samples is 9.3. But then how much did they vary between the calls? So this is like less than a 1% difference, right? Which is good. But if you are seeing that going to 100%, for example, then it means sometimes it was running at 9 milliseconds, sometimes it's 8. And so there's a lot of variance. And then you should question whether these are reliable figures that you can depend on. But yeah. So what happened is last year, my whole take on those spawning processes and how fast can be in Python changed when I purchased this piece of hardware. It's a $9 little Internet of Thing device, 80 megahertz CPU with a little wireless controller, running MicroPython. And it really impressed me because I can run my Python on this machine, and I slapped together through some examples a Python-based web server, and it works great. So then that made me explore Python more. And I saw that, so what is MicroPython? It's a lean implementation of Python 3. It has a more limited collection of libraries, but at the end of the day, when you write code in MicroPython, it's just like regular Python, functions and variables and lists and dictionaries. And the cool thing about it that I discovered is that you can run it and compile it for any Unix platform. So on Linux or Windows, Linux or Mac or BSD. Then I wanted to just point out a few libraries that ship with MicroPython that are very useful. usocket, that will let you open UDP, TCP connections, start a TCP server so you can basically run a web server on it. UOS, this will let you spawn processes, collect their output. So, and then a bunch of stuff like JSON, regular expression, time, and compression. So that just makes it a nice candidate for maybe getting rid of some of these bash scripts when startup time is a point of concern. So just for reference, this is where I run the benchmarks on this hardware that I purchased last year. It's basically running Ubuntu 16.04, and we use the latest version of Python 3.7 and MicroPython. So these are the results. So when we run that little add.py simple one-line script, you see the one thing to take away from the slide is that Python is way slower relatively compared to all these other interpreted languages. It's over 9 times slower than the fastest one, like awk, right? The other thing is that you can you can spawn a process, a Python interpreter, MicroPython, right? It can read a Python script, interpret it, execute it, do the output, all in less than a second, in half a millisecond. So that was an eye-opener. I wasn't aware prior to doing this exercise that there were options like that. So the next slide, it's again taking the same information, but now looking at the CPU cycles. And this kind of shows where the delay is coming from. It's because it's more CPU intensive, right? Python 3.7 compared to MicroPython. Another thing to make note is when I ran this on older versions, it took more than 9 milliseconds for us. So Python 3 has gotten faster. They do care about startup times. And I want to emphasize it's not that 9 milliseconds is ages. It's just to know that there's that cost and how it works relatively. So that's the end of the first part of the presentation. In the second part of the presentation, we will look at just a real functioning implementation of using MicroPython to make something useful, right? Because it's fine to see the numbers, but how does MicroPython code actually look like when you're trying to execute something that's useful to you? So what we will do is we will implement our own pip bash completion using MicroPython. And let's look at what comes with pip itself, right? So pip has a feature to let you do bash completion. But the thing is, if you just import pip itself and you see, okay, how long is the import of it, let alone getting to the code, that on this machine is taking more than 700 milliseconds. On my previous machine, it's taking more than a second. So from a usability perspective, you want anything in the terminal that you're typing to be very interactive. You want those responses to be under 100 milliseconds, right? Also, the built-in pip completion, it'll only complete the subcommands, right? It's not going to go and say pip install and list you the package names dynamically, right? So the version that we're going to create, it's going to connect to, I've created a local mirror of a bunch of Python packages. So I have a web server Nginx running with 400 wheels. And what it will do is, as we write pip, and we do tap to get our auto-completion, it'll complete the subcommands, but it'll also complete the package names and the version numbers. So every time you press tab, it does this. It's live. The moment you add a new package to the web server, it will automatically appear in your auto-completion. These are just some of the environmental variables that I've set to have pip look at the correct web server. So I won't go into too much detail about this, but this is basically one of the ways that you can do bash, auto-completion. And so it's just specifying that for the pip command, call this bash function pip completion. And the point of note is the pip-comp.py, right? That's our actual little Python script that will be doing all the work. And it receives one argument, comp cword, which argument is it completing? So when you write pip, and then after pip, the first argument, it will say number 1. So that's install, freeze, or whatnot. And then the second argument would be the name of the package. So let's look at the code. So the first line is just pointing at the MicroPython interpreter, like you would with Python or whatnot. And then I'm using 3 packages. uRequests is just like the request library, but for MicroPython and UOS and sys. So this is the heart of the bash completion. Nice 3 lines of code in the function. The first line will connect to the web server, retrieve the HTML, listing all the wheels. The second line will parse that HTML and extract all the names of the wheels as a list of strings. And then finally, because the wheel specification separates the name and version number by dash, we can just use that split by dashes to extract the name and version. And at the bottom here, we're just looking, are we completing the first or second argument? And we'll print either the subcommands or the list of packages. So that's the whole code. When we run some performance tests to see, okay, how well does this perform compared to the built-in pip? The built-in pip we saw just importing takes 700 milliseconds. Here, when you're just showing the subcommands, it will do that in 1.3 milliseconds, which is way below our 100 milliseconds that we desired. And then in the second one, it's completing the package names in 9.1 milliseconds. So this really blew me away when I first looked at it, because it means that it's spawning this MicroPython interpreter, executing your script, connecting to a web server, parsing the HTML, spitting all this out in 9 milliseconds. So yeah, the performance is great, not just at the initial startup time of the interpreter, but even when you're using a lot of its packages. Keep in mind, I've noticed with Python, part of the slowness can be when you start at the interpreter. The others, even when you import some of the libraries, they can take time. But yeah, so let's do a live demo. Okay, so the first thing we're going to do is make a clean, fresh virtual environment. So we can run pip freeze. And you can see it doesn't have anything at this point. So now let's just take our little pip comp command for a spin. You see pip comp, when it's given that I want to complete the first argument, number 1, it shows the subcommands. When we say number 2, it's connected to the web server and fetched all of these requests. So let's just pop open our web browser. And we'll see that Nginx is hosting all these wheels, serving all these wheels. You have Django, Click, and whatnot. So I just took a bunch of wheels as sample data. And so you see we have 410 wheels that are being served out from the web server. So now let's actually try and install something. So first, when you do pip, right, if we press tab now, you see it's completing for us the options, right? I can do S, and then when I do this, it's only showing the options that begin with S. Let's try and do install. So at this point, it's showing 410 possibilities. So those are the same 410 wheels that we saw earlier, right? So let's start with C, see what we have available with C. You can see that it's showing all the packages start with C. We have Click, Colorama, and all the different versions as well. So let me go in. I'm going to install version 1.0 of Click. And it properly escapes special characters. Equal signs are special characters for Bash. So now it's installed, version 1.0. Let's install Colorama. We can run pip freeze, see what we have. Great. And let's upgrade pip to Click to the latest version, 7.0. And we'll just see that it's done that. Great. So now we're running Click 7.0. That was just a quick demo of the features. So you can find the slides for this talk and slides for other talks I've done on my website, marwano.com. And that's the end of the talk. So I'll just open the floor for any questions that you might have.